Hi everyone. Let's start today's session on Monte Carlo. So we'll be studying everything from what is Monte Carlo, why is it being used in the field of quant finance, what are the basic steps that are involved in Monte Carlo. We run a number different simulations in Monte Carlo, so how to arrive at what number of simulations to use, limitations, advantages, disadvantages of using Monte Carlo method, and what is the key difference between using a Monte Carlo method and other numerical methods, concept of risk neutral valuation and how it applies to the field of Monte Carlo. We'll be also covering how does central limit theorem supports the use of Monte Carlo methods, and then like the significance of law of large number in Monte Carlo simulations. We'll also see how to simulate assets, how to simulate different asset price for a stock using geometric Brownian motion, and how does Monte Carlo plays a role into that. Then, of course, like which all places can we use Monte Carlo and where should we use it? And also Monte Carlo has been used to do parametric to find the parameters or estimate the parameters of the quantitative models. So how to do that? So there's a lot of stuff. So let's start. Let's start this exciting session. So I hope you can see my screen. So Monte Carlo simulation. Okay. So you might think, right, what is Monte Carlo simulation and how has it been used in the world of quant finance, right? What is? So I'll refer Monte Carlo with MC, okay? So what is Monte Carlo simulation and how is it being used in the world of quant finance, right? So basically, to answer your question, so first we'll see what is Monte Carlo. So Monte Carlo is a computational technique, okay? So Monte Carlo is a computational technique which is used to solve a problem that involves uncertainty or complex dynamics. It is particularly used in areas where closed form solutions are difficult to either they are difficult to derive or there are no closed form solutions. So we'll be talking about what is a closed form solution, but this was like why do we use it? So Monte Carlo is basically a computational technique used to model used to model and solve financial problems that involves uncertainty. Either it involves uncertainty or there's a lot of complex dynamics involved in the process. Okay. So where do we use it? It is particularly useful in areas where closed form closed form analytical solution is difficult to derive. So, so what is an analytical solution? You might be thinking, right? What is an analytical solution? So you might heard of all these terms ODE, PDE, right? ODE is ordinary differential equation, differential equation. PD is partial differential equation. Do you guys know the difference between ODE and PD? Should I cover this?
Yeah, may
Guys,
you please
should I?
continue.
Okay. So, so the basic difference between ODE is If you see, let's say we have a function, okay, f of x, which depends on y, okay. So, or let's say we should, yeah, okay, something like y is equal to 2x squared plus 4x minus 2, okay. So here if you see, y is dependent only on one variable, right? But if the same equation was something like this, y is equal to 2x square plus 2z square minus 4a is equal to 0, let's say, or yeah, minus 4a, that's all. So if you see here, y is dependent on a, x, and z. So when your function, okay, let's say your function is dependent on only one variable, which is in this case x, right? It's called ODE, okay? And when your function is dependent on more than one variable, here three variables, then we use PDE to solve this differential equations. Okay. So if you see in ODE, we use we say dy by dx, right? But in PDE, partial differential equation, we say dou y by dou x, dou z, dou a, which is basically nothing but we are measuring the change in y with respect to these parameters. So when your function is dependent on more than one variable, that's where you use partial differential equation to solve your equation. Otherwise, you will use ordinary differential equation. So this is what we say as ODE and PD. This is what we say as analytical solutions. So a lot of times we have analytical solutions to solve, or let's say to derive to come up to a final solution to a problem. So, but if in case we do not have any ODE or PDE, let's say there's a financial problem and we cannot solve it using any partial differential equation or differential equation, that's where we use the concept of Monte Carlo. Okay. Also, if you see Black-Scholes model, right? You might have heard a professor saying, okay, let's derive the PDE of Black-Scholes model, which, and if you might have seen this formula, C is equal to S ND1, right? Minus K E R T ND2, right? Something like this you might have seen, right? So this is nothing, and this is, sorry, T minus T. Okay. So this is nothing but uh, your your Black-Scholes equations to price a call option, right? So in here, if you see, this is what we say as PDE. So if you see here, we have a equation to which can be used to arrive at a price of European call and put. But what if we do not have any equation? So that's where we or let's say if what if we cannot derive PDE, let's say ODE, right? So that's where we use the concept of Monte Carlo. First, did you understood this thing? Okay, I
Yes.
cannot hear you. So I mean, I cannot see anything on the screen. So just you can speak up if you understand. Just say okay. Yeah, we understood. Okay. So applications of Monte Carlo. Okay. You might be thinking, okay, it's okay. Where do we use actually Monte Carlo in the world of quant finance, right? So I'll refer quant finance as QF. There are there are so many places where we use the knowledge, or let's say the application of quant finance. First, option pricing. Okay. And I'm just covering the basics. We'll go into deep. Okay. So Monte Carlo simulation is actually used to price options where the payoff is dependent or on the path of the underlying asset. Basically, the payoff is dependent on the path of underlying assets price over time. So basically, if you see, Monte Carlo is used here. Okay, Monte Carlo is used here for pricing options. Okay, where the payoff depends on the path of the underlying asset. Okay. Example of this is Asian option. If you see, what does Asian option says? Asian option is nothing but it says your ST, your stock price, is nothing but your average of the path of the stock. Okay. So if you see any Asian option contract, what will happen is either they'll just, so let's say this is your 1 year period, right? So they'll just mention, okay, so what you do is, yeah, so what you do is take the average of the price after every 3 months, or whatever the contract says. So you'll start with some price here, let's say 100. Here it's 101, 102, 99, 98. So here you'll take average of all these prices to find. But the question is, how do you arrive at these prices, right? That's where we use the concept of Monte Carlo to arrive at these prices. So once we take the average, that's where you get the stock price of Asian, like the price of Asian option, right? And then we know how to arrive at the option price. All of us know maximum of ST minus K comma 0. So we have ST from this, right? We have the value of strike price already mentioned in the contract. So we can just arrive at the option, the call option price, right? So that's how we use Monte Carlo, that is to simulate the price of the stock, right? At different and then basically calculating the price of the option. This is the first use case. Second, risk management. If you guys have heard the topic value at risk, right? Value at risk. One of the ways of solving value at risk is using Monte Carlo methods, if you remember, right? So, so in general, Monte Carlo is used a lot in risk management. So it is basically used to assess the risk in the portfolio under various scenarios. So what we do is we basically simulate the returns of the asset in a portfolio under numerous market condition, and then we find the value of value at risk. Okay. So so what we basically do is we simulate the price of the stock, right? Then we calculate the returns of the stock, then arrange the returns in ascending order. Why do we say ascending? Because if you arrange the returns in ascending order, you'll get the worst loss first, and then maximum profit here, right? If you arrange the returns, right? So let's say -5%, -4%, this is all your returns. And then in the end, your maximum, whatever your maximum return, let's say 10%. So you'll arrange your returns like this. And then depending on what's your time horizon, right? What's your confidence interval, you'll calculate the value of var. So that's like one way. That's where this is like one of the ways where you can use Monte Carlo in value at risk. But like this, there are multiple cases wherein you can use Monte Carlo. One more application is if you have seen stochastic interest rate modeling, right? So what we do is we generate lot of interest rate paths, right? Using the method of Monte Carlo. Using the method of Monte Carlo. And this can be further used to either price any instrument, or maybe used for sensitivity analysis, scenario analysis, lot of different applications. But this is just to give you an example. Okay, Monte Carlo is also used in not just in option pricing. Okay, here we are talking about option pricing, but also it's also used in risk management.
Mehul, I have a
So
doubt.
and
In value at risk in Monte Carlo, we do, I think so, we simulate the returns, not the price of the stock, right?
okay. So if you see here, I'm written simulate the price of the stock.
Yeah.
If you see, right, um, if you If you remember the geometric Brownian equation, right? Do you know what is a geometric Brownian equation?
Yes.
Okay. Basically, it's something like this: dst, okay, is equal to mu st dt plus sigma st dwt. This is what we say as geometric Brownian motion. When we solve this, we arrive at this equation: s uh, t plus delta t is equal to st exp mu minus sigma square by 2 delta t plus sigma zt. So what we are essentially, if you see here, what we are essentially doing is we are using the geometric Brownian motion to simulate the stock price. Okay. And once we have once we get something like this, right? We'll have, because what Monte Carlo does is it will generate a lot of different stock prices, right? Something like this, almost like a close to whatever you want, million the million paths for stock prices. So then what you do is you calculate the returns like this. So you do not model the return using GBM, but you model the stock prices using the geometric Brownian motion. Okay, we'll be covering this. Okay, don't worry, we'll be covering this here in the today's session.
Thank you.
So moving on. Okay, moving on. What are the steps that have been? So I hope you understand. This covers our first question: what is Monte Carlo and how it's been used in the world of quant finance. Okay. So moving on to our second question. Okay. Or second topic. What's the, or let's say what are the steps involved in Monte Carlo? Okay. Okay. Let me help you with this. So as we know, there's simulations that has been involved in Monte Carlo, but it's not like we'll just use simulations. We need to understand what the problem is. Okay. So first is define the problem. Where are you? Why are you using the method for Monte Carlo? Right? What's the problem statement? Is it to price any instrument? Is it for risk management purposes? We also use Monte Carlo for portfolio optimization. So what is your purpose, right? Define the problem. So once you define the problem, right, construct a mathematical model of the system. So what do I mean by a mathematical model, right? If you see here, right, if you see in this equation, this was basically the equation that we got, right? So this will be a mathematical model for the system. If you see similarly, right, if you see Vesi-check interest rate model, Vesi-check interest rate model. What is the equation? I guess it's something like this. dRt is equal to AB minus RT dt plus sigma dWt, right? So this is, so if you see this, so this is basically our mathematical model for the system. So you need to construct a mathematical model for the system. Third, okay. Third is generate random simulations. Okay. So what do I mean by generate random simulations? Basically, what I mean by that is, um, because you should use a random generator or basically a random simulations to produce input for the model. Okay, and these inputs should reflect the uncertainty and the distribution of the underlying variable. Okay, so basically use a random generator or random distribution, whatever the case is, right? to produce the inputs of the model. To produce the inputs of the model. Now, these inputs, if you see, these inputs should actually reflect the uncertainty and the distribution. Uncertainty and, sorry, and the distribution, okay, of the underlying variable. Let me give you a quick example of this. Example, if you see geometric Brownian motion, right, which is used to model stock prices, right? Model stock prices. So in this case, what we assume is we are generating. How do we generate random samples? We generate random samples from our normal distribution. So this is our underlying assumption. I mean normal. So this is our underlying distribution that we say we are using for Monte Carlo, right? So if you see here, which is ZT, right? So we will be simulating. Sorry, we will be simulating ZT. How? Using normal distribution. Okay. So this is basically you simulate um you simulate using normal distribution. Next step is, and you can use any distribution, not just normal distribution. For geometric Brownian motion, because stock price follows normal distribution, that's why we use simulations from normal distribution. Now, after doing that, you need to run the simulations. And what do I mean by run the simulation is after let's say you generated 1 million simulations, right? So now you will use these simulations. So let's say every time you will you will you will use the value of ZT, right? And you already have all these values, right? You already have all these values. So you'll be using the value of ZT to generate a path, right? So if you are simulating for 1 million times, so you will have 1 million paths, okay? If you're generating 1 million times of ZT, so you'll have 1 million parts of Z, 1 million parts of stock price. Okay. So run the simulation. I hope you understand. Then aggregate the results. So what do I mean by aggregating the result is, see, after you have simulated, let's say 1 million times your stock prices, right? Now it's time to aggregate the result. Okay. So what I mean by aggregating the result is you need to compute mean and variance for this for your stock price. Okay, you need to compute mean and variance for your stock price. So what will happen is not just sorry just give me one second, sorry. So what will happen is now in each case now in each case what you will do is you will do st minus k, st minus k, this is st minus k. You'll basically sorry and maximum of you'll basically apply the formula for call option, right? Or put option or whatever option you're considering, right? So so now you will get certain prices here, right? Let's say 0.5, 0, 0, 7, let's say 0.7, 0.8, something like that. So now you will take average of this. Okay, you will take average of this to calculate the price of the option. So that's what I mean by aggregating the results. Okay, and the last step is analyze the output. Um, so so you need to understand, you can also compare this with the market data, change, different distributions, change the parameters, stuff like that. So the end thing is analyze the results. So I just want to summarize it again. Okay. The first step is you need to define the problem, why we are using the Monte Carlo method. Second thing is construct a mathematical model of the system. So this is Bessie check. Similarly, you have different interest rate models, or let's say we can also use geometric Brownian motion, which I just showed here to simulate the stock price. Um, don't worry if you don't know this equation, we'll be covering in today's class, okay? So, we'll basically construct a mathematical model for the system. Then after constructing this equation will generate here will generate the random simulation and how will we generate by either taking some assumption that we are taking the random samples from a normal distribution, and after generating, let's say, the simulations, right, you will use those simulations to run the model. Okay, so this can be also said as run the model. Okay, after you generated the simulations, you just run the model with those generated simulations, and then in the end you aggregate the result, because once you generate the stock prices, here you will get 102, let's say 105, 107, 104, 102, something like that, right? Some or the other you'll get in the end, right? So then you just need to apply the formula, and this is, we know that for a call option the formula is maximum of st minus k comma 0, right? So you just apply this formula and then uh, take the average of it to calculate the price of the option. I hope you understand this. Did you understand this? What are the steps for a Monte Carlo simulations?
Yes.
Yes, sir.
Okay, thank you. Moving on, you might be thinking, Mehul, you said Monte Carlo, we generate different simulations, but how do you decide? How to decide the number of simulations? Okay, right? That might be a genuine question that you might have. And the answer to this question is, see, some practitioners some practitioners use a thumb rule, okay, based on the specific based on their specific requirement. So what they'll do is they'll say, okay, let's run 10,000 simulations, and then start increasing it, and then see how the result is getting how the result is being how the result is changing. So this is basically a thumb rule. You can say, okay, let's start with 10,000 simulations, increase it to, let's say, 1 million simulations, and check how the results are varying, right? So this is either one way, or what you can do if you want to understand what you can do, how how it's actually done is, see, okay, but before telling you the actual formula, what I want you to understand is this thing. Okay, choosing the right number of simulation is very crucial. Why? Because it affects the accuracy of the results, and it also affects the computational cost. See, what will happen is, let's say if you say, okay, I want to run 1 million simulations, right, for my financial model, right? Or let's say for my quantitative model. You should also understand this also takes time, right? And we are in a world where, trading has been done in milliseconds, right? So if your system is even taking 2 seconds of time to run the simulation, this is computationally expensive for people who are working at for traders who are at high frequency trading firm or trading firms, right? So that's why you need to understand uh, how much simulation you should take. That's why this question, what's the number of simulation. Also, one more thing is, as we increase the number of simulations, right, the accuracy of the accuracy increases. So let's say our problem statement was, okay, let's price European option. Let's price um, Asian option, let's say, okay? So you might see that when you ran 10,000 simulations, let's say 1,000 simulations, versus when you ran 1 million simulations, the price that you will get using these many simulations will be more accurate, okay? And why is that the case? We will cover this. There is a concept of law of large number, okay, that we will be covering in the session. So because of this whole concept in statistics, because of this is like very important in statistics. So that's why we see like when we run more number of simulation, our results are more accurate. But the question is how to decide the simulation, right? So so the perfect way is, okay, um okay, one thing is, when you run simulations, if you run more and more simulation, let's say if you run more and more simulations, accuracy will definitely increase. Okay, but with this your standard error, or let's say your error, will also increase. Okay, your error will also increase. So now there is a trade off, what to do. Should we increase the accuracy, because this will also increase the error, right? So the answer to that is, if you see the error, or let's say the standard error, okay, this is proportional to the square root of n, where n is the number of simulations. Okay. So basically, to check, you need to plot, basically, let's say the mean, or let's say the variance, and check, how much is it stabilizing after a point. Let's say you chose 10,000 simulations. You got some mean value, and similarly, you got some variance value, right? So after doing this, you ran, let's say, 20,000 simulations, or let's say 50,000 simulations, 1 million simulations. After a point, let's say after this point, you will see there's nothing that is been getting changed in the mean value, right? But the variance is increasing, right? So let's say you are running 1 million simulation, you will see that the mean is the same as, let's say, this point, this place, you know these two are same, but here the variance has started increasing. So you will basically make a plot. So you'll see how, where is the, like basically of mean and variance, and check, like, till what point the mean is getting stabilized. So if after a certain simulation the mean is stabilized, right? The mean is stabilized, and if you see that the variance is increasing, that's where you need to stop the simulation. You need to stop the simulation. So I hope you understood this concept, but error is directly proportional to the inverse of square root of n. So as soon as you increase the n, if you increase the n, the standard error will also increase, right? So this is like the concept of this whole topic, like how many simulations should we take? Any doubts on this question?
Hello, hello. Am I audible?
Yeah.
So I have a doubt. Like in this case, how you define the error? Like it is the difference between the prediction versus actual.
Um, so see, the thing is, in this case, right? Error, if you see mean and variance, these are statistical measure, right? So we'll calculate the variance of this whole. Okay, let me tell you. Just give me 1 second. Let me plug in my charger to the left. Yeah, perfect. So what will happen is, so if you see here, right, you took the average of this. Similarly, you'll also take the variance of it. So you will arrive at some number, let's say 0.002. Okay, by taking like what is the variance of this. Similarly, you'll have multiple, you'll be running multiple simulations and then check what is the mean and variance of it, of your final value, right? And that's where you will realize, okay, after this, after let's say 50,000 simulations, my mean is just the same, but my variance is increasing. So I feel like, 50,000 now is a good number of simulations to consider. So if someone asks you, how many simulations to do, so you can always say that a rule of thumb is to start with 10,000 simulations and then increase it. And once you increase it, you should look at the mean and the variance. There will be a point when the mean will get stabilized, but the variance will start increasing. and that's where you have to stop it, stop the simulations. Did you understood?
Yeah, I understand, but like, the stabilization of mean can be understood, like, but how we can understand like how the variance would increase if we increase the simulate number of simulations.
Pranam, your voice is really slow. Can you say that again?
Hello, now.
Yeah, yeah, now it's better. Can you say that again?
Yeah, I was saying that like stabilization of mean can be understood like for the increasing number of simulation, but how variance is increasing with the number of simulation that I cannot understand.
Because this is how Monte Carlo works. So when you increase the number of simulations, it will also generate some error in the process. So that's
Uh,
that's where we say, it's a trade-off. Basically, when you
yeah,
increase your number of simulations, it will also increase your error. So that's why people say you need to find a trade-off between between your accuracy and your variance.
all right, got it, got it.
Also, just to help you understand it visually, so let's say you'll have 1,000 simulations, 1 million simulations, 50,000 simulations. What will happen is, um, as you as you uh, as you you know as you increase the number of simulation, we know, like, of course the variance will increase, right? But your mean, let's say we are plotting two graphs. Okay, let's say number of simulations and mean. Let's say something like this. But after a point, it's a constant value. The mean will not change, but the variance will increase. Understood? So in this case, the mean is constant, but the variance start increasing. That's where you should know, okay, I need to stop it. Okay, guys, understood?
Yes.
Yes.
Okay, perfect. Moving on. What are some of the advantages and disadvantages of using Monte Carlo methods in quant finance, or let's say in option pricing, right? Say what are some of the advantages and disadvantages of using Monte Carlo methods, okay, in quant finance, let's say. So one is Monte Carlo. So let's talk about the advantages, right? First, see, Monte Carlo method can handle a wide variety of exotic options where closed form solutions are not available. If you see, Black-Scholes have a closed form solutions, right? But if you see other options, it might or might not have any closed form solution. So I guess that's where we can actually use Monte Carlo method. So this mostly includes path dependent options, in which those options which have, like, which is totally dependent on the path of the stock. So in such cases, Asian option, barrier option, right? In which path of the stock is very important, because in Asian option you take the average of the path of the stock. In barrier option, what you see is, so let's say this is the barrier. So let's say you're simulating something like this. So if it reaches the barrier, that's when the it will get exercised. So all those places where, the path of your stock is very is dependent on your price of the option. That's where you use Monte Carlo a lot. So basically, Monte Carlo can handle wide variety of exotic options, okay, where closed form solution is not defined. Okay, so this is where you can use. That's where, Monte Carlo is really useful. Second is, see, we talk a lot about, we use Monte Carlo for risk management, but if you see, even in industry, they use it to, model different sources of risk. So it's also used to model different sources of risk. So what are some of the sources of risk? If you see volatility, right? So that's why if you see we use Monte Carlo methods and stochastic volatility models. Example of stochastic volatility model. It's fine if you don't know this, but I'm just letting you know, like, volatility is one of the biggest source of risk, right? If something happens, if the market becomes volatile, that's where, you need to predict what's going to happen. And that's where, Monte Carlo can play a big role. So we have a lot of stochastic models, right? Like local volatility model. Then we have Heston model. Then we have Saber model. So these are some volatility based models. So this can be, we can use Monte Carlo to, predict like what will be the future volatility. Similarly, we can use Monte Carlo to predict what will be the future interest rates. I guess you all know how much interest rate can affect the financial markets, right? So that's where we have, if you see, we have different stochastic interest rate models, right? Like Check, CIR, Hull White model, G2++ model. In all these cases, if you see, we actually use Monte Carlo method to generate or to simulate the different interest rates here. Yeah. So, so risk management is one of the most application. Monte Carlo is also useful in places where we have non-normal distribution. So what do I mean by this is, if you see, we always say, okay, stocks follows normal distribution, but what if it doesn't follow normal distribution? That's where Monte Carlo, can actually be used to model the stock prices. So, so all those places where you don't want to consider normal distribution, you can use Monte Carlo simulations. So, so basically, Monte Carlo can be used here to model stock prices, even if even if it doesn't follow normal distribution. So, so if you see, it's such a big thing, right? I mean, Monte Carlo can do such so important things. So, so these are, some of the what do I say? Some of the advantages, like you can use it for option pricing, wherein we do not have any closed form solution, and we can use it to predict uncertainty, that is volatility. Interest rates we can use to, predict the stock price, even if it doesn't follow normal distribution. But again, with that, we also have certain limitations, right? We also have certain limitations. That is, it's computational intensive. As I said, if we are running, let's say, 1 million simulations, it will take certain time, right, to run this. And not everyone can afford the computational cost. When I say computational cost, it's not for the software or hardware. It's about the time it takes to run the whole process to finally arrive at the price, because, markets are moving in milliseconds. So that's why it's like computationally intensive. Second is, it also, see, we, because Monte Carlo, if you see, what we are doing is we are generating random numbers from, so from some distribution, right? Let's say from normal distribution, or we can use other distributions also. But because we have this we generate all these random numbers from distribution, that's where that's where this can cause an issue also. What if your distribution doesn't follow the underlying, right? So even if you are able to use Monte Carlo method, but you will not arrive at a good accuracy, because place from where you have generated the numbers, random numbers, it's you have not taken the right distribution. So that is one of the issue that Monte Carlo can face. So that's why, like, understanding which distribution to take, and that's where, understanding of statistics. We have all this different distribution of, like, student t distribution. We'll be talking about it in this session only. So this is one of the issue with, Monte Carlo. Also, if you see, we know that we also spoke about um, the convergence, right? Accuracy, right? We know that as we increase the simulation, I mean, um, the the variance will, the variance will also increase. So so that is also one of the issue, because if, let's say, if you see variance, right? If you have variance is nothing but, let's say, standard deviation, right? So if you have, let's say, how we say is mean plus minus standard deviation, right? That's how you arrive at a price, right? From statistics, if you see mean plus minus, if, let's say, this number is really big, let's say 0.2, so, and mean is, let's say, zero point 0.8. So if you see something like this, if this happens, right? I mean, these are just random numbers. So in this case, standard deviation is really high. So it's very important to reduce the variance, right? So variance is also one of the, I mean, disadvantage, that even though you can generate a good amount of simulations, but with every simulations you generate, your variance, or let's say your error, will also increase. But despite these limitations, Monte Carlo is highly used in the industry because of its robustness and versatility for pricing different complex derivatives, and also used a lot in modeling different risk scenarios. Okay, moving on. Let's understand. Do you have any questions on this? Okay, I'll take that as
Pardon.
no. Yeah, yeah, please ask. Is there any question? Okay, let's understand what is the concept of risk neutral valuation in Monte Carlo, right? How do we basically use risk neutral valuation? First, can you guys tell me, or can you all tell me, do you understand what is risk neutral valuation? Anyone who wants to try this? Sarthak? Okay. No worries. See, risk neutral valuation is fundamental concept in the world of derivatives. You see, professors always telling us, we always consider a risk neutral world when we are pricing derivatives, right? Or even industry folks speaking on, yeah, let's consider the risk neutral world. But what is a risk neutral world? Okay. So basically, risk neutral basically means that all investors are indifferent. All investors are indifferent to risk. Okay. So what does this actually mean? What this mean is the expected return on any investment is the risk-free rate of interest. Okay. Risk-free rate of interest. So what does this means? Oops. Risk-free rate of interest. So what does this means? So example, if we are in a derivative, if we are in a neutral, if we are in a risk neutral world, Apple and Microsoft, and let's say Bank of America, all will give me the same return, which is what? Risk-free rate. So that's why we say investors are indifferent to the risk, because we assume in the risk neutral world, or in the derivatives world, that everything will grow at the same pace, that is at risk-free rate. This is a very important concept. Okay. So let's see the step-by-step application of risk neutral valuation in Monte Carlo. Okay. So first thing. So how do we use it, right? Let's see step-by-step application. So let's see step-by-step application of risk neutral valuation, right? In Monte Carlo. So first thing, we'll be modeling under risk neutral measure. Okay. And what does this mean? Let me tell you. See, when you use Monte Carlo to price any option, the very first step is to simulate the future path of the underlying asset, right? So, so in the risk neutral valuation, what we expect is all these stock prices, or let's say all these paths, they are modeled in such a way that the expected return on these assets is nothing but the risk-free rate. Okay. So if you see, um, if you see the equation of geometric Brownian motion, right, which is nothing but dst is equal to mu dt plus, okay, sorry, mu, we can also write this as mu st dt plus sigma st dwt, okay, under the risk neutral world. So if you see what is the mu is called the drift. Drift is nothing but the expected return, right? So for all the cases, right, we'll just replace the drift by the risk-free rate. And this is done for all the derivatives. So whenever you are using geometric Brownian motion to simulate the price, right? Or let's say to simulate the price, right? You'll be not using the actual returns of the stock. Instead, you will be using the risk-free rate, and this is a very important step, okay, which everyone should know. Okay, so first thing is you replace the drift by the risk-free rate. Then second step is what? You basically generate random numbers from normal distribution, right? This is nothing but your dwt is nothing. You'll generate dwt using normal distribution. Okay, and after you generate it, the next step is, of course, as of all of us know, what's the next step? Anyone? Compute the value of derivative, right? See, it's very, it's very straightforward. See, once you have, let's say we have stock price, right? We'll simulate, first we'll simulate the random numbers using the random numbers, right? Once you simulate the random numbers, we'll consider this as a risk-free rate. We have the stock price, we know the time, we know the standard deviation. So using this, we'll get this, right? So we'll have different values here, right? Now since we have the stock price, just how will you compute the value of derivative? Just use the payoff equation. For call option, it's nothing but maximum of st minus k comma 0. So let's say if in our case, let's say k is 99. Okay, so here will be what? 100 minus 99, maximum of 100 minus 99 comma 0. So this will be what? 1, right? So here we'll get 1, 2, 1.8, 0.9, zero point 0.9, right? And then what's the next step? Compute the mean and variance, right? So after you get this, you compute the mean of this to arrive at mean is nothing but average. Okay, you compute the average of this whole prices, that is 1 to 1.8, zero point 0.8, zero point 0.9, whatever it is, right? You compute the mean and the variance of it to arrive at the price of the option. But didn't you understood how the only assumption that we changed here is instead of taking the actual returns, when we consider risk neutral world, we always take this as risk free rate. Okay, so always make sure whenever you are pricing any derivative for that matter, you always use risk-free rate. You are not using the actual returns. And one more step, which is, of course, because if you see, this is simulated almost for an year, right? This is like if you see the time frame is 1 year. So the last step is, let's say, you discount the price, okay, which I forgot to write up. But what you do is you discount the price, okay? Let's say price of the option. This you discount, okay? So this is so we okay. So this is, let's say, the payoff, right? Different payoff we get from simulations. So what you will do is you will discount the payoff, okay? You will discount the payoff, okay? And then take the mean of it to arrive at the price. Did you guys understood this or not?
Mehul, we need like we are using this to for the derivative purpose, right? That's what you told me, correct?
Okay. Sorry, can you say that? Can you say that little
So,
loud?
so what's the use case of using this risk neutral? I mean, like in real
Measure.
world, my concern is on that, right? Reason being, like with different security, you are equating the same with the risk-free
Right.
return, right? So,
Okay, I
yeah,
understood. I also had the same doubt when the professor told me how dare people taking the same returns on different stocks, right? I mean, how dare them? So you see, the thing is, I mean, pricing derivative is already complex. Okay, so that's where all these researchers, mathematicians, when they started pricing it, because just imagine, right? If let's say we say, okay, let's try to model Apple, then let's try to model Microsoft. The returns that it will generate, this process become very, it becomes very challenging. Even if you can say, oh, let's take last 3 years data to find the returns, okay? But if you see, this also have some correlation with this part, right? So this whole process of generating the actual returns becomes very complex for pricing any derivative. That's where researchers, mathematicians, all this finance professors, I mean, whosoever wrote, I mean, whosoever came up, they came up, okay, let's take a risk neutral world. In that risk neutral world, we'll say all the stocks will grow at risk free rate. But see, it's an assumption. Like if you see other models also, we take certain assumptions. So even in the world of derivative, we take the assumptions of risk neutral for all the product. We assume that for option pricing, we'll assume that the drift, or let's say the return, is nothing but the risk free rate.
got it.
I hope that answers your question.
Yeah, Mehul.
Perfect. So let's see what is. Okay, how many of you know the central limit theorem? Okay. So central limit theorem is basically a concept in statistics that really plays a very important role for maintaining the reliability on the concept of Monte Carlo. Okay, the central limit theorem states that the average of the average of large number, okay, the average of large number of independent identically independent random variable with finite mean and variance will approximate to a normal distribution. Okay, let me write this and let me explain you this concept. So central limit theorem states that the average of large number of independent, okay, okay, let me write independent identically distributed. So what do I mean by this is IID, independent identically distributed, okay? So the average of a large number of independent identically distributed random variable with finite mean and variance will approximate to a normal distribution. Okay, first of all, how many of you actually knows what is independent identically distributed? Should I explain this concept?
Yeah, man, please.
Okay. IID, independent identically distributed. So what we mean is when we are generating different paths, or let's say when we are generating a random number, okay? Because if you see what is IID, we have a random variable, right? So when we are generating random numbers, right? So let's say 0.0.05, 0.7, 0.2, 0. Whatever it is. So first of all, it should be independent. So this value should not affect this value, should not affect this value. And that's why we say it as random, right? It is totally random. So this is what we mean as independent, that one should not affect the other. Identically distributed basically means they should be from the same distribution. Okay. So identically distributed basically means they should be from same distribution. We know that when we say, okay, we are generating random numbers from normal distribution, right? So we assume that all these numbers that are being generated will be generated using normal distribution. From, the underlying distribution will be normal distribution. So this is what we say as IID. That is, it should be independent and should be from the same distribution. Now, so when we say that all this random variable which has been generated, we say um, if they are, if we do the average of that, let's say if we do the average of it, the final distribution that we come will be a normal distribution. Okay. Um, so now how this is important for the world of, or let's say for the Monte Carlo. Okay. So if you see what we do in Monte Carlo is we basically what we do is we simulate so if you see Monte Carlo, right, what do? We take some assumption that let's generate the random numbers from let's say normal distribution, right? That's our assumption, right? So when we generate, so let's say we generate 1 million simulations, 1 million random numbers, right? We'll use our equation, right? And we'll plug in these values in our equation to calculate the stock prices, right? We will have multiple stock prices. So what we say is when we take the average of just the stock prices, right? So the distribution that it follow will be normal distribution. So let's say if we plot a histogram, do you all understand histogram? This figure, right? So if you see, this is nothing but if you plot a histogram for all these prices, you will find normal distribution. The underlying distribution is normal. And that becomes so important, right? I mean, um, because we always say, okay, stocks follows normal distribution. So that's why this concept of law of large number, that is, if you're simulating random numbers which are IID, which basically independent and are identically distributed, then the average of that will follow a normal distribution. So that's why central limit theorem, okay, that's why central limit theorem is used to justify Monte Carlo method. Okay. So that's why we use central limit theorem to justify the Monte Carlo method. Okay. Did you guys understood this concept?
Yeah.
Yeah.
Okay. Perfect. So basically we are generating large number of independent identically distributed random variable with some mean and variance, right? With some mean and variance, and that will approximate to a normal distribution. Okay. So if we arrange all this, it will approximate to a normal distribution. Now, what is law of large number? How many of you really know what is law of large number? Any idea?
I mean, like I know in that sense that if the larger the number, then the mean of that will be more accurate in sense.
Yeah. Hmm. Perfect. So, what is the significance of large number? Law of large number. Basically, law of large numbers is again a statistical concept, which basically says that as the number of trials in a random process increases, basically as the number of let's say if the number of random, let's say if you're simulating random numbers, right? If that increases and increases, right? Let's say from 10,000 we take 20,000 to 1 million, right? Simulations we do. So what it says is when we do the average of the result, right, that we obtain from those simulation, it will actually converge to the expected value of the random process. Okay. This is what law of large numbers is. Let me help you understand this in a better way. But let me write the definition, okay? So basically law of large number states that the number of simulations in a process if okay, sorry, if the number of simulation in a process increases. Okay, sorry for the writing. Okay, if the number of simulation in the process increases, right? And then if we do the average of the result, right? So when we do the average, right, from these average of the result, it is most likely that the result will actually converge. Converge means basically the value will be very similar or very close by, okay? The result will actually converge to the expected value of the random process. So this is this theorem of statistics, right? Law of large numbers is a statistical theorem, right? Which basically says as you increase the number of simulations and if you take the average of it, it will come very the average that you have received, right? It will be very close to your actual, to actual value of your system, right? This is so important for Monte Carlo, right? Why? Because if you see in Monte Carlo, what we are doing, we are running the number of simulations, and that's where I said, if you remember in the beginning, if you increase the number of simulations, your accuracy of the result will actually increase. So I told that from where, but where that they that but from where it came is using the law of large number. This is why these two things, theorems, these two concepts of statistics, that is sorry that is law of large number and central limit theorem. These are very essential for Monte Carlo. Okay, did you understood it? Any questions?
Mehul, I'm just thinking more broader. I mean, देखिए मैंने सेंट्रल वो सॉरी मैंने मोंटे कार्लो सिमुलेशन रन किया, मेरे पास कई लाइंस और रिजल्ट्स आ गए।
हम्म,
मैंने मीन और वेरिएंस किया, मैं मीन एंड वेरिएंस से को प्लॉट करके क्या कुछ हम जनरेट नहीं करते हैं क्या? आई एम जस्ट थिंकिंग जैसे फ्रंटायर वो नहीं होता है ऑप्टिमल फ्रंटायर, राइट? तो जिसमें आप
हम्म।
देखते हो कि एक आफ्टर सर्टेन पॉइंट फिर रिस्क बढ़ रहा है पर रिटर्न उतनी तेजी से नहीं बढ़ रहा है। तो नोइंग दैट कि मोंटे कार्लो हमने रन किया, हम हमारे पास मीन है, हमारे पास वेरिएंस है, वी कैन प्लॉट सेम थिंग एंड उसके ब्रॉडर कुछ कर नहीं सकते क्या? आई एम जस्ट थिंकिंग फ्रॉम दैट सेंस।
Okay. So here is the thing. Why we are doing this whole process to arrive at a price, right? See, when you know some options, key, what's the correct value of the option? That's where all these traders, risk managers, they take actions, right? So so let's say if you use Monte Carlo to generate uncertainty, let's say interest rates, or let's say you use Monte Carlo to generate what is the future volatility. You saw, okay, the end result came in, the future will be highly uncertain, highly volatile. So, the interest rates, let's say the volatility will be highly volatile. So you as a risk manager will communicate this to your different desk, right? You might communicate it to your derivatives desk, fixed income desk. Volatility of, let's say, this product is, let's say, option pricing, right? So you'll say to the derivative trader that the volatility in the market in the coming days will be really high. So you need to start hedging, or hedge your positions, or start selling whatever you have, right? Depending on which position might hurt the organization's, right? So it's not like, oh, okay, okay, we have arrived at this number. It's, see, modeling is just one part of it. Intuition of what has arrived is very important. So you should always understand, okay, let's say Greeks, right? We also use Monte Carlo method to estimate the value of Greek, delta, gamma, rho, theta, vega. Let's say delta is 0.5. What does it? It's not like, oh, delta is 0.5, we have arrived at, but what's next? Next is how to use that number for your benefit, right? That is that is what is important too. So I hope I answered your question.
Yeah, Mehul, I got the point actually. So it's more like एक बार number आ गया, then how you are going to interrupt that particular thing, right? For other part of the business, I guess, right?
Yeah, I mean, see, pricing is just one part of it, right? Now, with pricing,
Yes.
there are other for certain steps that you have to do. If you see, we do all the traders do calculate, Greeks, but that is not the only thing that they do, right? I mean, risk managers, if you see, they also understand, okay, this, okay, delta is this, rho is this, gamma is this. We need to do this, right? So then the strategy steps comes into place. What's next? Let's build a strategy, or let's say, we have to, so there are a lot of things that goes into place, but modeling is like the first part of it.
Got it.
Okay. So, uh, any other questions from anyone else? So, moving on. Just give me 1 second. Okay. So, you might be thinking, we spoke about, Monte Carlo can be used to handle non-normal distributions of asset, right? So you might be thinking how to handle non-normal distributions of asset, of, let's say, stock price of whatever your asset is, right? Using Monte Carlo, right? See, Monte Carlo does a really, it's very important for accurately modeling the real world behavior of the financial assets. Okay. It is not necessary that all the returns, let's say, the asset, or let's say the stock, or whatever your asset is, it follows a normal distribution. It's not always the case. It can follow some other distribution. If you see during the pandemic, right? COVID time, right? 2020, the stocks were equities were not following this normal distribution. So what how can Monte Carlo helps into this? So the way Monte Carlo can help is basically, n- there are methods to address non-normal distribution in Monte Carlo. Okay, so how Monte Carlo does is basically, instead of assuming a normal distribution for the return, right? It basically use other distributions too, which can be modeled using Monte Carlo, right? Because as I said, we are generating the random numbers from using a normal distribution, but we can also generate the random numbers using some other distribution, let's say a student t distribution, any other distribution. So let's see. So basically, if you see, instead of assuming normal distribution, Monte Carlo plays a really important role to capture the properties. Okay. When I say capture the properties, I mean like if let's say you find out that okay, your returns are not normal distribution, so you can use student t distribution. So what is a student t distribution? Basically in student t distribution, the tails, right? If you see this is a normal distribution, right? This will be your student t distribution, right? So if you see the tails are thicker in this. Okay, so if you see tails are thicker in this, so when tails are thicker, that or let's say when the tails are heavier, that means it is more flexible for modeling the returns with higher kurtosis, right? So similarly, we can also take some other distribution, let's say log normal distribution, or let's say let me pick another one, which is let's say stable Paretian distribution. So you can use this distribution specifically for heavy tails, and if your asset if let's say the returns are highly skewed, okay, if these are the two condition, then you can also use stable Paretian distribution for modeling your asset. Then of course you have a lot of distant distributions that you can explore, but this is like one of few ways of if in case your distribution is not normal. Second way, Monte Carlo helps us. It helps in transforming the normal data. Basically what it does is basically there are few methods, which is like variance gamma model, or let's say non-inverse Gaussian model. And what it does is it basically generates scenarios where returns are modeled by a process that generalize Brownian motion to include jumps. Okay, I'll give you one example. So this is the first thing. This is on the distribution side, it helps. Okay, now we see let's how to transform the data, how to transform normal data, right? See, you might be thinking, I mean, stocks, sometimes you see jumps in it, right? Sometimes you see jumps in it. Like what happened if you see in the COVID period, right? There was a sudden decline, right? So how to accommodate that stuff? So you can actually do that using Monte Carlo. So there's a process called variance gamma model. Okay. So what this approach does is it basically generates scenarios where returns are modeled by a process that generalize Brownian motion to include jumps. Okay. Now these jumps are very common during the time of distress. Okay, distress market condition, or when we see okay, there's something happening there's some volatility in the market. So this is like one way. The other way is using, let's say, normal inverse gamma Gaussian model, sorry. So basically, this is a distribution capable of handling.
Mehul, sorry, one thing. I mean, like, अभी एक हफ्ते पहले, I was talking to one of the fund manager. Okay, he's a quant fund manager. India में he's quite famous. So they
Mhm.
were telling that कि even at the time of COVID, so I mean they were talking about some trend shift mechanism. तो क्या that जो आपने A option बताया है, is that the same? Like where I mean where data were telling them the trend is shifting. I guess they told me trend shift model, something like that. So is it
See,
something?
See, these are on the distribution side, right? I mean, see, there are a lot of distributions, a lot of different models. It's on the person who is modeling it. Abhi, someone who's a quant, he has more of a mathematical and statistical background. So he'll try to, model it in that terms, maybe mathematical or statistical terms. Someone who's let's say who's from a commerce background, who's not great with mathematics or statistics, he'll try to use some other models, right? So it's more of depend on person to person and organizations, to be honest. But in big organizations, I've seen people using Monte Carlo methods a lot. I agree, most of the times we do use normal distributions, but this is, I'm just telling you, how Monte Carlo is useful. People might use, people might not use, right? But this you should understand how it's being used, how it's so useful, and and why is it being used by the industry.
Okay, got it.
So basically, normal inverse Gaussian is basically a distribution which is capable of handling symmetry as well as the heavy tails. So guys, because we are on time, there and I still need one more class. Um, Basically to to make you understand the rest of the processes. But do you have any doubt up till now? Can do you have any doubt? Let me open my camera. Yeah, do you have any doubt as such? Did you understood what is Monte Carlo, how it's being used? Or can you just tell me how did you like this topic? Did it help you in any way, Sarthak?
Yes, I would say that it was completely like a different perspective of Monte Carlo, because I used to just think a lot Monte Carlo towards value at risk, but I was, after learning all this, it's like really diverse, and I really like the thing.
Okay, I guess Janelle, have you studied Monte Carlo back in your masters?
Yes, I did. Yes, I studied
But
it.
yeah, did you understood today's concept?
Yes, it was really systematic, I feel, and it was easy to understand. Like I
Mhm.
feel when I was in class, like in my masters, like the professor used a lot of jargons. I was getting really
Mhm.
confused and it was difficult to understand even if I tried to understand. But
Okay.
I think a lot of my concepts did get cleared, but I honestly I feel like I need help trying to understand how to fit all of these formulas, in the code.
So
So
here is the thing. In our next class, we'll be doing a practical implementations, because I said, okay, geometric Brownian motion and stuff like this, we'll use it. But of course, when you understand how it's being used, utilized in the code, so I'll be actually coding it in the next class. That's why I want to stop this class at this moment, because I want to have another 1 hour and 30 minutes of session, that in which we'll be actually working on how to utilize Monte Carlo for pricing
yeah, that
different
would be
options.
yeah, that would be really nice and it would be great because I feel like one of my main issues is like actually, putting it in a code, like
Okay,
figuring it out
don't
in a
worry.
code.
It's way too simple. Way too simple. Understanding the concept is hard, but putting inside the code is way too easy. So don't worry on that.
Okay.
Other J, I guess for Anikesh and Srujan, it's like the very first time. Let me stop the recording. Just give me 1 second.